So good afternoon or good night, good evening to everyone. Welcome to the CRM Applied Math Seminar. Today it's our pleasure to have Sheehan Olver from Imperial College London. He'll be our speaker for today. So Sheehan got his PhD in 2008 from University of Cambridge under the supervision of Riesz. And then he moved quite a lot. Actually, I was quite impressed by the movement and even before that, he was in Minnesota to do his undergraduate studies. And then after Cambridge, he was a junior research fellow at Oxford for 4 years. And then after that, he spent a year in Hong Kong, or he was a visiting fellow there. And then he spent, I think, a year at Oxford again. And then he was in Sydney in Australia for something like 6 years, like from 2011 to 2017. And since then, since 2017, he's a reader at Imperial College London. So very impressive trajectory. And well, today is our speaker. So please, Sheehan, the floor is all yours.
Thanks. So I'm talking on spectral methods for solving equations involving power law kernels. So here we're sort of thinking of integral operators of the form of sort of a convolution form. And really, we're sort of focusing on the case. So this is a linear operator acting on U. We're focusing on the case where this sort of involves a sort of power interaction. So the idea is and I'll sort of describe some motivations in a second. We want to solve equations involving such integral operators. And the idea is to develop spectral methods in a certain way so that we turn this continuous non-local operator into a sparse discretization, which can be very easily solved. Okay. This is joint work with my PhD student Timon and Jose Carrillo, who was up until this year at Imperial, but has now moved to Oxford. So this was really, this work was sort of motivated by taking something I had done 2011 for log kernels and generalizing it for the case of power law kernels, which turn out to be significantly more complicated. So what's the motivation? So this is just this is a cartoon. This is don't take this seriously. But and I've always wanted to give a talk with a bunch of birds and say something like that. But this is sort of the hand wavy motivation. Is so you can think of birds as sort of particles. Now they obviously can't go too close together. So there's sort of a repulsion that the birds try to stay apart, but also they don't want to get too far apart. And so there's also an attraction. So we can think of birds as sort of attractive repulsive particles. And what one sees in practice is that one gets these sort of like equilibrium distributions. We want to sort of understand that, at least in an idealized version of it. Or for a more apropos example is people who obviously want to stay together, but are forced to not be too close together. And so we could sort of, in the sake of, if we're going to do fictional examples, we could also do this fictional example. Okay. So we can sort of think of this as a simple interaction of point particles. So this is a simple point particle model. Don't ask me anything about it, but this is fairly standard. We sort of have forces acting on the particles. Some of them are self-propulsion, friction. Background potential is often there. But really the thing we're most interested in is this interaction potential, that the particles themselves interact. So if they're too close together, there's a force pulling them apart. If they're too far apart, there's a force pulling them together. Okay, so some examples, and we're going to sort of focus on these two examples. Electrostatic is a logarithmic repulsion. So think of electrons on a wire, they repulse. You could sort of describe their dynamics using this equation. And if there's a background potential preventing them from going too far apart, they'll reach an equilibrium. The more interesting case is this attractive-repulsive case where we have two power law terms, one corresponding to, hopefully I got this right, this is attraction, and this is repulsion. Yeah, because log is negative. The first one is repulsive, so I think I got that right. Okay, so we have this simple model of particles that simultaneously attract and repulse. Okay, so let's see some, now this is a point particle model. We can easily do simulations. Let's just see what this looks like. So let's start with the classic electrostatic repulsion. So here we put down a bunch of particles in sort of, think of these as electrons on a wire. They're repulsing according to the logarithmic repulsion, but there's a background potential preventing them from going too far apart. So sorry. Let me see if I can. Okay, there we go. So this is the dynamics over time of these particles, and you see over time they reach an equilibrium. Okay, and so our goal so the problem that we're sort of interested in is describing this equilibrium, or more precisely, we can do a histogram of these point particles. This is sort of we can think of this as the limit as the number of particles tends to infinity, and as time goes to infinity, these particles will reach a steady state. Our question is, how can we describe this curve, or how can we compute this curve, the equilibrium distribution of these particles?
So
this case,
a question. Sorry to interrupt. I have a question. So what you did in the movie that you showed, so you started with what? With a few number of particles, and then you started to increase the number of particles. And how did you do that increment? How did you, if you want to, did you start from scratch your initial value problem, or you kind of took the output of your simulations, you kind of, I don't know, in a specific way, you added some particles, and then you started from there, or you always started from initial condition?
That movie was just one sample. So I started with, let's say, 1,000 random particles, evolved it in time until they reached equilibrium.
Oh, I see. So you did not play with the number of particles.
No, but then the theorem is a theorem as the number of particles tend to infinity. So there's sort of two limits there. We're sort of thinking of the steady states for n particles, and then what are the asymptotics as n goes to infinity.
Mm-hmm.
Okay.
Thank you.
And this case is very classical. There's a whole book by Edsaf and Todic, I think. So and this is sort of potential. This is very close to, this is sort of potential theory type stuff, because it's like a logarithmic potential. Okay, but so this case is classical. In the case of where it's just quadratic potential, it's known, and it's been known for a while, that you get a semicircle. Okay. So that the distribution has a sort of square root singularity. So that's a sort of log kernel case. What if we look at this attractive-repulsive case? Well, again, we get something very similar. So the previous movie I did, this movie my student did, so that's why it looks different. But this is, again, starting with, say, 1,000 particles. At each time step, it's plotting the histogram, as well as, so on the bottom, you can see the particles themselves evolving in time according to this attractive repulsion. There is no background potential in this case, because the attractive repulsion dynamics is enough to contain the particles. Okay, and we see with this particular choice of alpha and beta, the particles go into a distribution, and the interesting thing is that this distribution actually blows up at the endpoints. Okay. So we get very similar type behavior, but with different types of singularities, different distributions. And again, our question is to figure out what this red curve is. Okay. Now, for some more interesting case is now I think we've left alpha the same or roughly the same and just changed beta. And now we see that we get quite different behavior. And now, so ignore the red curve. The blue curve is this limiting distribution. And we see something very interesting. We again have a limiting distribution, but in this case, it's supported on two distinct intervals. So you can sort of think of this in this flock of birds example. This flock of birds has somehow separated and it's created two disjoint clusters of birds. Okay. So our question again is to compute this blue curve. So fortunately, there's a nice description of what exactly this blue curve is. I think it was red curve before, then it was blue curve. And essentially, we want to find a measure that minimizes some sort of energy. So here, mu is our unknown. We want to find the mu such that this is minimal. So here we see our kernel, which can be the log kernel or the power log kernel. And here we see sort of an external potential. So that's an external potential. Sometimes zero. So sometimes we have this, sometimes we don't. Okay, so our goal is to find mu. Okay. So if I was a normal numerical analyst, I would start everywhere I see an integral, start replacing sums. And it looks pretty miserable trying to do that because it's optimizing over a space of measures. I don't think that would work very well. Fortunately, I'm not a normal numerical analyst, so I'm not going to discretize integrals at all. I'm going to leave them as integrals. Okay. So instead, I'm going to use something that, and this sort of goes back to work with Alex Townsend in 2012, and I think he gave a seminar here, here as in the cloud, but in this, the fake Montreal, I guess. He gave a seminar in the fake Montreal, where we came up with this idea of, and this is kind of amazing that it translates into this very different setting, but so for ordinary differential equations, which are actually local operators, very different from these sort of convolution integrals that we're sort of talking about, we came up with this approach of turning general ordinary differential equations, including with variable coefficients, into very sparse linear systems. And the whole idea was using sort of ultraspherical orthogonal polynomials. After that original work, we went on to generalize it to rectangles, disks, and triangles, so PDEs. But more relevantly, and this was with Slavinsky, so Slavinsky, and who's in Manitoba now. I don't remember the year, 2016. We also saw that it worked for singular integral equations. So this approach of turning ordinary differential equation to a sparse linear system, of choosing bases in a certain careful way, also worked with these non-local operators, singular integral operators, which I'll go into details shortly. Okay. And so our goal for this talk is to take these techniques that work very well for ODEs and PDEs and singular integral equations and sort of generalize them for these power law kernels. Okay. So I guess there's two big themes here. One is work in coefficient space. Don't try to work in physical space at all. Try to choose a basis to sort of induce this structure, the sparse structure in the operators, to convert these operators, whether they be differential operators or singular integral operators or power law kernel operators into, in this case, banded matrices. The second theme is don't try to discretize. As soon as you start discretizing, it makes things into a mess. Okay.
Small question. So you're talking about, so these, I mean, you will probably say that, but let's say now you've shown us some example in 1D. So do these methods of ultraspherical and banded coefficient space and all of that, does that apply to higher dimensional problems as well?
Sorry, I missed the end of your comment.
Oh, sorry. So, you know, you showed us essentially up to now some one-dimensional interactions model.
Yeah.
So do these techniques, will they also apply to higher dimensional problems?
Yes, with radial, in the radially symmetric case.
Okay.
So if you, now, not all distributions you see are radially symmetric, so that's a big catch, but it's sort of the same in the analysis.
Okay, yeah, got it. Thank you.
Sorry, I think there's something, can you hear me okay? Okay.
Yes.
Okay. Okay, great. Sorry, your side is a bit flaky, but I guess that's fine. Okay. So yeah, so partial differential operators we have working on sort of simplices and non-radially symmetric domains, as well as things like this. These techniques will probably only work with radially symmetric domains, but that's a big open question. Okay, I'm not going to talk about higher dimensions in this talk, but we do sort of have a proof of concept working. Okay. So this is sort of the outline of the rest of the talk, is I'm going to go through the ultraspherical spectral method for these different equations. So starting with ODEs and PDEs very briefly, and then talking about log and Cauchy kernel singular integral equations, which is a bit more straightforward. I'll describe how these techniques also work for equilibrium problems, beginning with this potential log kernel case. And then finally, I'll get to the power law case. Okay. So our goal is to take an ODE, and here's a very simple example of, oh yeah, this is an example from Lee and Greengard of a very hard to compute equation, but it's meant to be just sort of a general or second order differential equation. And our goal is to convert it to a sparse linear system, which we can then efficiently solve with, say, millions of unknowns if necessary, and then therefore recover the solution. And the way we're going to do this is to write U in an expansion, well, in this case, a Chebyshev expansion, but discretize the system using ultraspherical polynomials. So some, and then the second step is sparse linear algebra, which we can do efficiently. Okay. So just for some notation, I'm not going to go through the full theory of orthogonal polynomials, so it sort of suffices to think of the definition of Chebyshev Tn of x. This is going to be our basis. This is a polynomial of x. It is, of course, cos n arc cos x, and it's orthogonal on -1, 1 with respect to this way. Now, to get the sparse discretization, we can't just use this basis. We can't just apply the differential operator to this basis. We also need to use its sort of derivative, which we're actually going to define as the derivative of t. Of course, it also has a nice definition of sine m+1 arc cos x over sine arc cos x, but it's sort of more natural to think of it as the derivative of Chebyshev t is Chebyshev u. Okay, and these happen to be orthogonal with respect to square root 1 minus x squared. But this also works to higher orders, that if we differentiate un, which is cn1, we get cn2, which we just define as the derivative. So cn lambda is defined as the derivative of cn lambda minus 1. these are all polynomials and they're orthogonal with respect to this sort of hierarchy of weights. Okay. Okay, so, but basically we think of this un is a derivative of tn, cn lambda is a derivative of cn lambda minus 1 up to constant. Okay. To make, because recurrences are very hard to read, especially in a short talk, to make the notation simpler, I'm going to use this, what's called a quasi-matrix notation. So really, these are sort of like, think of them as row vectors of functions. So we've taken our basis, our Chebyshev t, our cos, and our cos x, and just put it in a row vector. Okay. The reason this is a nice way of thinking of a basis is that if we have a function u of x that we've expanded in Chebyshev expansion, we can write this in this sort of very clean notation of this row vector times a infinite vector of coefficients. Okay. So we're going to use this sort of language because you'll see in a second that it makes a lot of the relationships between differential operators and other operators and bases easy to write. Okay. Sorry, I don't know what just happened. Okay. Oh, I have to use my finger. It depends on my finger. So just by the definition, so remember we said un, we defined it as a derivative of tn. We can write it in this very clean way, and we can almost think of it as sort of a commutation relationship that if we hit Chebyshev t on the left by d dx, it's the same as ux times this. Similarly, and this is just by definition, it's rewritten the definition in a cleaner way. So derivative operators become these very sparse operators. And then of course you can compose them. So if I want the second derivative of tx, that's just hitting this by d dx and composing these two matrices, and we get the second derivative as a sparse, almost diagonal matrix. Okay. So this gives a very clean way of working with bases and changing continuous operators into sparse linear systems. And the nice thing is this also works for, say, the identity operator. Now, if the derivative is changing bases, that means identity needs to also change bases, but we can use sort of recurrence relationships. These are sort of classical, and really they sort of come up from trigonometric identities to say that tx is equal to ux times the sparse matrix, and so on. And that should be t. Okay. So this gives a very clean way of converting. So here's sort of, we can think of it in terms of this diagram. Each of these operators is sparse. This is, for example, tridiagonal. This is sort of a classical result for orthogonal polynomials, that they have tridiagonal three-term recurrences. So we can think of the operator multiplying by x as sort of x times t of x is equal to t of x. And then I'll call it J for Jacobi operator, where that's tridiagonal. Every time we differentiate, we get a sparse relationship if we change bases. And then, of course, you can sort of compose these. Okay, so that's sort of the idea. So let's see sort of how these pieces all fit together. So if we want to solve this ODE, this example that we had, we represent u of x in this basis. This operator, by these sort of relationships, translates into this system. And so we just need to invert a sparse system. Well, I forgot boundary conditions, but let's ignore that for now. Okay. So that's sort of the general idea, is that we cook up these sparse relationships applied to these sort of families of orthogonal polynomials, and then we're able to turn solving a differential equation into a sparse linear system. Okay. And these have a lot of nice properties. They're stable, they converge fast because they're spectral methods. We can handle more complicated variable coefficients. I just had X there, but you can do higher, more complicated things. You get adaptivity really easily, and they're pretty nice. Okay. Now, these have very similar methods. There's a long history of this going all the way to Crenshaw in the 50s. I don't have time to go through the full details of how this differs from previous stuff. They're very similar, but one nice thing is this approach, as we'll see, generalizes to other operators. Okay. So just very briefly, I won't go into any details, but the same techniques work for partial differential equations. So here if we want to solve, for example, this variable coefficient Helmholtz equation on a triangle with, I guess I said with zero Dirichlet conditions, we can use a basis of orthogonal polynomials on a triangle. So here on the right, you see our computational domain. It turns out partial differential operators X, Y are all has sparse representations if you're careful about these bases. And therefore, by using a very similar trick, we can convert this PDE into a very sparse linear system, which can be solved efficiently, and we can solve PDEs on, say, triangles. Okay. And you can do more complicated things, but let's move back to integral operators. Okay, so that's sort of the gist of how this approach works for ODEs. Yeah?
Okay, I actually wrote my question in the chat in case I was not going to be clear enough on if my voice was not going to be clear. But so is that what, do you know if that's what Sheehan is using to solve ODEs? This kind of
no. So this is what Approximate is using. Sheehan uses it. So there's a long story. Sheehan is still using collocation, so you can't do equations with millions of unknowns. But if you solve PDEs on a rectangle, it is using this. So there's this funny thing is the fastest way to solve an ODE in Sheehan is to write it as a PDE on a rectangle.
I see. Okay, that's great. Thank you.
Yeah, but they don't have the version on triangles implemented it. So this is all implemented in Approximate in Julia, including on triangles. Well, as sort of like an add-on package. So, yeah.
Okay, thank you.
Any other questions before I move on? All right. So now we want to see how these ideas of using a basis built out of orthogonal polynomials can work for other types of operators, such as singular integral operators. So here's sort of the gist of what we want to do is, here's an example application, which would be some PDE on, this is sort of an exterior problem. So we want to solve a PDE off some geometry, and using sort of the standard techniques, you can recast solving a PDE to solving a singular integral operator on sort of the boundary of the domain. Okay, so really we're interested in, and this is going to involve log kernels and say Cauchy kernels or Hilbert kernels. Okay. So using this same idea of applying the operator to basis built out of orthogonal polynomials, we can actually translate this boundary problem to a sparse linear system and then get a solution to a PDE. So this PDE is something called the, so here you can sort of see these are the gammas, these sort of three intervals. Maybe I'll do it. We're solving a singular integral equation on these three intervals that tells us the solution to the PDE off the intervals using this sort of standard Green's integral representation stuff. And then once it's reduced to a single integral equation, we use this technique of creating a basis to convert it into a sparse linear system. Okay. So without going into the full details, the key thing we want to do is be able to work with these types of operators. So we have the log kernel operator, which is I think something I wrote earlier. Its derivative, which is just a Hilbert transform. And I'm not going to talk about it, but we could take it another step forward and do the second derivative of the log kernel is fractional Repulsion. Okay. So these are, and I'll explain where these come from in a second, but basically we end up with the same thing, that we can use a weighted Chebyshev basis. And when we apply the log operator, it's going to actually be diagonal to Chebyshev itself. And then of course, once it's in this ultra-spherical framework, we can then differentiate. So for example, the Hilbert transform applied to this basis has a sparse, we can write it as a sparse matrix times Chebyshev U. Or the fractional Laplacian is a sparse matrix times this C2 basis. Okay, so we basically taken what worked for ODEs and added this extra thing, the log kernel operator. Okay. So where does the sparsity come from? So a classical result for orthogonal polynomials, which presumably most people in the audience are aware of, is that any family of orthogonal polynomials satisfies a three-term recurrence. So now if we want to see what the Hilbert transform does, and remember here we have HU of x is this singular integral operator, integral 1 over pi over the support, U of t over dt. Okay, so my claim is that the Hilbert transform of the weighted orthogonal polynomials, that should have been the lowercase p, satisfies essentially the same three-term recurrence as the orthogonal polynomials themselves. So this is a very classical thing. It's in, say, Gauch's book. And it's very easy to derive it because if we want to find the three-term recurrence, x times h times the weighted Pn, we do sort of the usual trick that one does in analysis. You subtract something and add it back in again. So we subtract off t. That kills off the singularity. And add it back in. And now here to here is just the three-term from above. So I'm just plugging in this three-term recurrence up here. And we see that x times HWPN satisfies the same three-term recurrence as the orthogonal polynomials themselves, apart from this basis term. Okay. So that works for any OPs. Could be Hermite, it could be something non-classical. In the special case of Chebyshev, we have, it happens, I know why it happens, I'm not going to say why it happens, but it happens that the Hilbert transform of this weight is precisely 0. Why is this important? That's important because then when we plug it into this three-term recurrence, we get that the HWP naught is 0. That tells us that HWP1 is constant, HWP2 is linear. that tells us HWPN is polynomial. It's exact, so it's a polynomials that satisfy the exact same three-term recurrence as Chebyshev U, and so we get this sort of key result that the Hilbert transform of Chebyshev T n is minus un minus 1 of x. Okay, which in the sort of quasi-matrix notation says that this turns the Hilbert transform into a very sparse operator, sort of acting on coefficients. Okay. So that tells us where the Hilbert transform relationship comes up from. What about the log kernel, the thing that we were sort of originally interested in? Well, we have this nice property because this vanishes. I'm not going to go into any technical details, but Hilbert transforms are very nice to define on the real line for sufficiently continuous functions. This happens to satisfy it, and then you get sort of various other properties. For example, the derivative of Hilbert transform commute. So this tells us that the derivative of the Hilbert transform of that is the Hilbert transform of the derivative of that, and which tells us it's the Hilbert transform of Chebyshev T, which we know is equal to whatever I wrote in the last slide. So, so then we can integrate the relationship, and we get that the log kernel. So T is U is a derivative of T. T is the integral of U, and you sort of by integrating this, the UNs turn back to TNs, and we get this sort of nice relationship. Okay, so that's sort of the gist of the idea. Is just like derivative operators turned into very sparse matrices, so do log kernel operators and also Hilbert transform operators and also their derivatives using some key sort of orthogonal polynomial tricks. Okay. So one last thing, what about when you have, before moving on to the last part of the talk, what if you have multiple intervals? Well, if we think of the log kernel on one interval in this basis, well, we know how to do it on the interval evaluated itself. So the question is, what happens if we sort of evaluate it on a separate interval? Well, this is a very nice, smooth operator. It's Hilbert-Schmidt, it's a compact operator. So L gamma 1, we can think of it as restricted to gamma 2 is compact. And same with Hilbert transforms. Actually, log is, I should say, really compact because the log kernel on the interval itself is also compact. It was decaying, but so this one is really, really compact. Well, Hilbert-Schmidt, but actually much more than that. So this means that when we represent this in the spaces framework, these sort of cross terms are very well approximated by finite matrices. So in this quasi-matrix notation, the log kernel on sort of, if we represent the solution on each interval in sort of a weighted Chebyshev basis that's mapped, is sort of diagonal plus compact. Okay, so very efficient to solve. Okay, so that's how we can sort of do things like this, is each so on the intervals we use mapped Chebyshev, and then here we can do the same things with 4a and convert the singular integral equation defined on such a geometry to a very sparse linear system, well, diagonal plus compact. Okay. So that's so that's how you can solve singular integral equations. So now we want to go back to this, what we started with, which is the equilibrium problem. So for example, how does one solve this log kernel equilibrium problem? Okay. So remember, we want to minimize this energy. We want to find the measure that minimizes this energy, or equivalently, we want to find the measure such that on the support of the measure, we get our constant. Okay. So let's forget about this for now, because it sort of comes out for free. Let's just think of, how do we solve this? Well, if we know the support, so let's say we knew the support was AB, then this is just a linear solve. This is just L times, let's call this whole thing U of X. L times U is equal to V of X minus L. Okay. So this is really just a linear solve if we knew the support. Okay. Now we have this extra degree of freedom, but we also have this extra constraint that our measure has to be a probability measure. Okay. So this is enough. So I don't know how to erase, but so remember, this turns into a diagonal system. So we have a diagonal linear system. The one thing we don't know is the support, but we can solve that by an optimization problem. So we've turned optimizing over measures to optimizing over the support, which is just two unknowns. Okay. And this is actually something with modern automatic differentiation. This is something you can really just sort of plug it into a package and say, optimize this for me, and it works. So we actually can do this with optim.jl, the Julia package. Okay, so just by discretizing the operator, we sort of get this optimization almost as an afterthought with this ansatz of a weighted Chebyshev over the interval. I don't have time to talk about the other method, which is actually the one that I originally did. But that's okay. So now we can just sort of plug in a potential. And for any potential, we can automatically find the interval AB and the equilibrium measure. So if we did that sort of logarithmic point process with these background potentials and looked at the limiting distribution, they would look like this. Okay. And there's some fun things where it's almost always square root singularities, but for some degenerate cases, it's not. But I'm running low on time. Okay. Okay. I'm not going to say anything about this. The same technique works for multiple intervals, essentially doing what I said in the previous slide, which you have sort of the interaction on each interval itself. The sort of interaction between different intervals is compact, so we can still do the linear solve. And again, if we can do the linear solve, we can do the optimization, now with an ansatz of multiple intervals. Okay, so here here we see some simple potential that we're scaling by different amounts, and we can actually see that the supports change, but using this numerical method, we can rapidly calculate these measures. Okay. So I'm sort of rushing a bit because I wanted to get to the final stuff. Is now, how does this work for power law kernels? So not knowing anything about this problem, we would expect to use a weighted basis, but we don't know the singularities. We saw that we got some different singularities depending on alpha and beta. So let's say this is our ancestors, these ultraspherical polynomials, which have different power law singularities at the endpoints. Now, what one normally does is looks at the DLMF and finds some relationship and says, oh, that's the relationship that turns it into a banded system. Unfortunately, there's not much there. But so there's these really ugly expressions. They're not integrating over the right domain. It's only sort of power law, and it's not the right. It's not right at all. But it does give us a hint of using what's called fractional integrals. Okay. So to do the power law kernel, we're going to express it as a sum of a left and right fractional integral. Okay, so just decompose it by cutting in at the point of singularity. Okay. Oh no. What just happened? Okay. Okay. Now the nice thing is that trick for Hilbert transforms of subtracting and adding back in again also works for these fractional integrals. So for example, x times this left fractional integral, well, we do x minus t plus t, that's t times pn, that's just like the usual 3-term recurrence. We get this alpha plus 1, q of alpha plus 1, but these fractional integrals are fractional versions of indefinite integration. So we have this relationship that alpha plus 1 is alpha times the left integral of u. Okay, then for classical orthogonal polynomials, we get the left integral can be reduced back to this. But the key thing is we can put this together and get that this left fractional integral satisfies a 3-term recurrence. Okay. We can do this also for the right fractional integral. And it follows, putting everything together, these, I'm going to claim they're new, relationships for orthogonal polynomials, is that these power law operators satisfies this very simple 3-term, well, it's 2-term because of one of the terms is 0, recurrences. Okay, I'd say probably not because nothing in orthogonal polynomials is new. So it's probably in some esoteric Russian book somewhere, but whatever. Okay. So this works for, so if you notice here, we have two things. We have alpha, we have lambda. This result works for any choice of alpha and lambda, I think. How do we choose lambda? Well, we basically need to choose lambda, and this part is known what the right lambda is, so that the log, so just like the Hilbert transform of Chebyshev was 0, which means that the log transform of Chebyshev was constant, we need this to be equal to a constant. So we choose lambda so that the log, or this power law operator times the weight is constant. And unfortunately, this is known. And then from the recurrence, we get the key result is that the log is actually that. Okay, so exactly analogous to think the log kernel times weighted Chebyshev was Chebyshev times this diagonal thing. Okay. So this sort of generalizes that to from log kernels to power log kernels. Okay. Now I think I'm basically out of time. There were some restrictions on alpha, but we can also do alpha, and instead of diagonal, we get banded, but that's sort of just as good. Now, what about the case where we have 2? Fortunately, it's not banded, but it sort of exponentially decays off the band. So well approximated by a banded system. So basically, for these power log kernels, we can use this basis to turn it into a very sparse linear system. And therefore, that whole framework that worked for the log kernel case translates. Okay. So there's lots of open questions in this. The log kernel case is classical. There's essentially no open questions. For this attractive repulsive case, there's lots of open questions. There's some basic results, but this numerics allows us to do exploration and sort of understand some results. So let me just finish with one figure. So this was computed with our results. This is the, we've left alpha equal 4. I think the attractive term fixed. We're varying beta. And unfortunately, it's the slowest movie in the world. But this sort of shows us the transition from sorry, that's not working very well, but it shows us the transition from 1 support to two supports. And this is sort of calculated in our framework. Okay. It also showed some very interesting behavior. We're not sure whether this is real or just a numerical artifact, where when it transitions from 1 to 2, there's no singularity in the middle, but then eventually there forms a singularity. But anyways, so I'll stop there. We already mentioned radially symmetric. Other problems are hard. There's sort of connections with fractional Laplacians. So these techniques would also work for solving equations involving fractional Laplacians. And then I guess the point of the talk is to stop COVID, we need to forget about this 2 meters, and we just need to find the right alpha and beta to prevent prevent the spread of COVID. Okay, I'll stop there.
Thank you very much. Are there any questions or comments? Oh, I guess there was a question by Tim. Do you want to ask it, Tim?
Oh, this is outdated now, but I may as well ask a question, a different question. So at the very beginning, you presented like, and also later on, there's always an optimization problem over probability measures. Can you go to the slide, the first slide where you presented that? Because I mean, I'm just a poor optimizer, and I wanted to know the connection between solving all these different types of differential equations and that optimization problem. Yeah, that one, exactly.
Okay, so this optimization problem, I guess so the Euler-Lagrange reformulation is sort of the key. So the optimization problem is equivalent to this problem.
Oh, okay, right.
And then if we know A, B, and L, it's a linear problem.
Okay.
So that sort of yeah.
Okay, so you basically, but I mean, you're minimizing over mu in that formulation, the first line, right?
Yeah.
And then,
which is equivalent.
Go ahead.
Yeah, so that's equivalent to solving this equation, the Euler-Lagrange. So if we know L, A, B, it's a linear problem, and then we take as an ansatz a special form of the measure.
Okay, so that inequality disappears. I mean, there's an equality constraint, and
the inequality part, the greater than or equal to L, that will be satisfied provided that we have the right number of supports. So, so that's essential for the optimization. Yeah, it's sort of hard to describe, but if you have a constant on one interval, you know, basically that's more of a statement of the property of the measure than a criteria. But it is possible to get something that is constant, but not optimal if you get the number of supports wrong.
And where does the assumption that you always have measures with compact support come from? Is that well, you always want to, like, I mean, it's all scalar in your case, but I'm guessing you can generalize this to Rn. And then the question is, why does your measure have compact support?
Okay, so so in the log kernel case, it's sort of this is known. So so essentially what you can do is sort of so you don't need to assume it has compact support. As long as it satisfies those two properties, then it has to be the answer. So it's sort of the other way around. So you use this framework to you ignore the inequality. You use this framework to find the measure that satisfies the first equation, but you haven't actually verified that is the minimizer. Then to verify it is the minimizer, you check the second constraint, the inequality. But here we're taking it sort of as an answer. So in the power law kernel, there's a lot of open questions. Probably the compact support is open, depending on the parameters alpha, beta, but we can sort of work backwards and say, this is our ansatz.
Okay, thanks.
Damien, I believe you had a question.
Yes, I had a question. It was related to that diagram that you draw. I don't remember the page. It was about the sparse matrix, and you're applying like some kind of commutator at each step. So my question was like, yeah,
this one.
Yes, exactly. So that one. So it makes me think of some kind of differential complex. So my question is more like, is there any differential geometry inside behind this this problem that is playing well behind the scene, or that is probably related to some properties of your operator, this parallel kernel or something like that. So is there something of that level here, or?
Not that I know of. So I mean, everything in this talk was sort of 1D. So you wouldn't sort of imagine differential geometry coming up. Maybe for the stuff on triangles, there is, but yeah.
Okay. Okay. Thank you.
Right. Other questions or comments?
Yes, Olivier.
Yeah.
It's a small comment and a question linked with one of the theorems you mentioned. Do you do that also for the kernel of the Helmholtz operator in 3D? Because at one moment you showed us a slide on acoustic problems. And
yeah,
from what I
only
knew, but I did not refresh what I knew for a few years, for the high frequency Helmholtz, there are problems of the diagonal dominance. Do you have any new results on that, or are you aware of some or any other things like that?
But you're talking about 3D.
Yes, I'm talking about 3D. So
these
close to the acoustic you mentioned in one slide with the 2D with the two obstacles.
Yeah. So there you don't have in 2D this works fine. You have diagonal dominance.
Yes, because it's log, and so you have the decay in x minus y when x minus y is large for the derivative.
Right. 3D the only geometries where we would know how to do this are the spheres. So you can use spherical harmonics, and then the Helmholtz operator is diagonal, as it seems that you know. So then you could do this same approach with say many spheres.
Yes.
Maybe that I haven't looked at that at all.
Do you know the references for the results on the decay or not? Are you aware of some or not? Are you aware of references for the result on the diagonal dominance for this case or not?
On the log kernel case, the 2D case?
The 3D case.
Well, I don't know about the 3D case.
Okay. So never mind, thank you. And thank you for the talk.
Okay.
Okay, Miguel, I think you had a question.
Yeah, the restrictions you mentioned at the end for alpha and beta, do they come from the method or because you want a confining potential, or both?
So you mean these restrictions, alpha has to be between -1 and 1?
Oh, yeah. Well, for the power, for attraction repulsion one.
Which restrictions are you?
When you were talking about the attraction repulsion ones, you said that there were some restrictions on alpha and beta.
Do you mean this? So there's the results that are known analytically are only known for very restricted parameter regimes. So here in this slide, I sort of mentioned that. So and you can see this is very recent results, but you have sort of like very limited cases where things are known analytically. The numerical method works much broader than that. So I think the restrictions are just that alpha and beta have to be greater than -1. But I'd have to double check with Timon.
I see. All right. Thank you.
Right. Any other questions or comments? Actually, I have one. So in the movie that you were showing, the slowest movie in the world, as you said, it looks like, you know, there is this appearance of two local minimizers. And could you think of that as potentially a pitchfork bifurcation?
I don't think I know enough about pitchfork bifurcations to say anything intelligent, but sure.
I see. Okay, now because it looks like there is some sort of because you mentioned something that, you know, there is no singularity, or you mentioned something about singularity not being there, or.
Well, so the actual transition, this formation of the gap is completely open, the nature of it. So now our particle simulations, you can run numeric particle simulations, they match the results we're seeing. The catch is at that transition region, the particle simulations are very delicate because you'll have sort of one-off particles in the gap, which in the large n limits have have zero measure, whatever. But for finite n, they sort of just don't tell you a fine enough picture of the singularities. And we're actually, now the interesting thing about this movie, if it ever gets to the actual transition, is that in our basis, we're actually allowing blow up. So think of the log kernel case. We use 1 over square root 1 minus x squared as the ansatz. That allowed blow up, but the actual results were bounded at the endpoints. Okay, so there we saw the transition. So the interesting thing is, very briefly, it stayed finite. And that was coming from the optimization, not from us imposing the basis. What we are imposing is the nature of this singularity. There aren't enough analytical results to know that we've gotten that correct. It matches what we see in particle simulations. But yeah, there's a lot of questions here, but it's sort of, I guess one hope is that the numerics would sort of be a guide for new results in the analysis of this problem.
Okay, thank you very much. Are there any final questions or comments? Well, it's already, I believe it's already 10:11 p.m. in London. So, I mean, thanks a lot for having found the energy and time to give us a seminar at that time for you, Sheehan. So thank you very much. Unless there are other questions or comments, and I mean, I would like to thank you personally. And well, your talk will appear on the CRM YouTube channel actually in the next couple of weeks. So more to follow. All right.